A non-cancellation lemma for Goldman bracket. Arpan Kabiraj. Abstract. Given an oriented surface, we study the properties of two terms of the Goldman bracket between two free homotopy classes of oriented closed curves with different signs, when one of the free homotopy classes contains a simple representative. We prove that in the above situation, the geometric intersection number and the number of terms counted with multiplicity in the Goldman bracket are the same. Introduction. Let capital F be an oriented surface and x, y be two oriented closed curves in F, intersecting transversely in double points. The Goldman bracket of x and y is defined as square bracket x, y, close square bracket, equals sigma p, which are elements of x intersecting y, epsilon of p times angle bracket x asterisk subscript p y close angle bracket, where x times y subscript with x multiply subscript p y denotes the loop product of x and y based at p. X intersecting y denotes the set of all intersection points between them. Epsilon of p denotes the sign of the intersection between x and y at p in the positive direction of both axes, and x in angle brackets denotes the free homotopy class of the curve x. Goldman, in 1986, showed that this bracket satisfies the following remarkable properties. If x is freely homotopic to x sub 1 and y is freely homotopic to y sub 1, such that x sub 1 and y sub 1 intersect transversely in double points, then square bracketed x, y equals, this is the Goldman bracket x sub 1, y sub 1. The Goldman bracket xy is equal to negative Goldman yx. If x, y, and z are three oriented closed curves intersecting pairwise transversely in double points, then the Goldman bracket of the Goldman bracket x, y with z plus the Goldman bracket yz as a term with x plus the Goldman bracket of the Goldman bracket zx y, zx, the Goldman bracket of the Goldman bracket zx, comma, y equals 0. We denote, there should be some way to unambiguously state mathematics in speech, purely in speech. Anyway, we denote the collection of all free homotopy classes of oriented closed curves on F by capital script C, and the free module generated by capital script C by capital block Z of capital script C. Let angle bracket x denote the free homotopy class of a closed curve x. For any two elements, angle bracket x and angle bracket y in capital script C, we consider two representatives x and y of bracket x and bracket y respectively, intersecting transversely in double points, and define the Goldman bracket square bracket of angle bracket x, angle bracket y between angle bracket x and angle bracket y to be square brackets x, y. By the first property, the Goldman bracket is well defined on script C. We extend the Goldman bracket linearly on capital block Z of script C. By the above properties, the Goldman bracket is a Lie bracket on block Z of C. The pair block Z of C, comma, square bracket indicating that it should take a pair, denoted by capital script L of F, consisting of block Z of C and the Goldman bracket, is called the Goldman-Lie algebra. The structure of the Goldman-Lie algebra for surfaces of non-negative Euler characteristic is either trivial or well understood. See Cha 2010b, lemma 7.6 for the torus case. Therefore, throughout the paper, we assume F to be of negative Euler characteristic. By a paper published in 2011, Theorem 1.2, we can endow F with a hyperbolic metric. By a hyperbolic surface, we mean an orientable surface of finite type with negative Euler characteristic and with a given hyperbolic metric. Let angle bracket x and angle bracket y be elements in capital script C. Denote by I of x, y the minimal possible number of intersection points, counted with multiplicity, between curves representing angle bracket x and angle bracket y, which intersect transversely. The number I of x, y is known as the geometric intersection number between angle bracket x and angle bracket y, and plays a crucial role in low-dimensional topology and geometric group theory. In his paper, Goldman, in 1986, section 5.17, Goldman proved the following relation between the Goldman bracket of angle bracket x and y and I of xy, where angle bracket x contains a simple representative, a closed curve without self-intersections. Theorem 1.1. Let x and y be two free homotopy classes of closed-oriented curves in capital F. If x contains a simple representative and the Goldman bracket of x, y equals 0, then I of x, y equals 0. Goldman used the convexity properties of the Teichmuller space to prove the above theorem. In this paper, we proved the following stronger version of the above theorem using basic techniques from hyperbolic geometry. Main theorem. Let angle bracket x and angle bracket y be elements in C. If x contains a simple representative, then I of xy is the same as the number of terms in the Goldman bracket of xy counted with multiplicity. Remark 1. In a paper published in 2010, Chas gave a proof of the above theorem using combinatorial topology and group theory. She used HNN extensions and amalgamated products of the fundamental group of a surface to prove the theorem. Goldman discovered this bracket while studying the Weil-Petersson symplectic form on Teichmuller space. The Teichmuller space of F, denoted by capital script T of F, is the space of all marked hyperbolic surfaces up to isotopy. The Weil-Petersson symplectic form induces a Poisson bracket, denoted by curly brackets, on the space of smooth functions in Teichmuller space, each free homotopy class of oriented closed curve x on the surface F induces a smooth map L of x on the Teichmuller space, namely the length of the unique geodesic in the free homotopy class of x. Let x and y, not in angle brackets, be two oriented closed curves intersecting transversely in double points. The Goldman bracket x, y between them, and the Poisson bracket curly brackets L of x, comma L of y of their length functions satisfy the following relation, which Goldman showed in 1986, theorem 3.15. Curly brackets L of x, comma L of y is equal to the smooth map L of the Goldman bracket x, comma y minus 1/2 times the product of first quantity, the sum of p, which are elements of the intersection of x and y, of epsilon p, which is the sign, times the smooth map of x itself, the homotopy class, times the smooth map of y. So the sign is under the sigma, but not the smooth map. It's really tough to state this type of notation unambiguously. Where length is extended linearly on the right-hand side, Goldman used this relation in convexity results of geodesic length functions, which was presented in 1983 to prove theorem 1.1. Later, the combinatorial structure of script L of f has been studied. Cass and Grongold proved that for a compact surface with non-empty boundary bracket x, comma x cubed determines the self-intersection number of x. Using hyperbolic geometry, Chas and Gogdeal in 2014 proved that there exists a positive integer m sub 0 such that for all m greater than or equal to m sub 0, the geometric intersection number between x and y is the same as the number of terms in bracket x to the m comma y divided by m. Kawazumi and Kuno in 2013 used Goldman algebra to study the Torelli-Johnson-Morita theory. There is a Lie co-bracket defined by Turev on block Z of C, which is the dual object of the Goldman bracket. This structure has been studied. Idea of the proof. We use techniques from hyperbolic geometry to prove the theorem. Let capital X be any point in capital script C of capital F. Let x sub 1 be an oriented simple closed curve, and y sub 1 be an oriented closed curve. The free homotopy class of x sub 1, respectively y sub 1, contains a unique geodesic, which we denote by x, respectively y. We have the bracket x sub 1, y sub 1, which is equal to the Goldman bracket x, comma y. Given two elements of the Goldman bracket between x and y with different signs, we consider the lifts of the terms to the upper half plane, capital block H. If two terms corresponding to two intersection points are freely homotopic, then the length of their geodesic representatives with respect to x is the same. We use the geometry of the product of geodesics in the upper half plane, capital block H, to show that the angle of intersection in the positive direction of both axes at both intersection points must be the same. This should be true for any capital F in script T of F. We use Fenchel-Nielsen twist deformation to construct a new point capital Y in script T of F, where the angle of intersection is different, which leads to a contradiction. The main ingredient to show that the angles are different is presented in a paper published in 1983, Proposition 3.5. Organization of the paper. In section 2, we recall some basic facts from hyperbolic geometry and Teichmuller space. In section 3, we recall various definitions of Goldman bracket and their equivalences. In section 4, we prove that it is enough to consider the problem for closed surfaces. In section 5, we describe the lifts of two terms of Goldman bracket which are equal and have different signs. In section 6, we give the proof of the main theorem. Acknowledgements. The author would like to thank Siddhartha Gadgil for his encouragement and enlightening conversations. The author is supported by the Department of Science and Technology, DST, Inspire faculty. Preliminaries. In this section, we recall some basic facts about hyperbolic geometry, hyperbolic surfaces, and Teichmuller space. References for the results mentioned in this section are the following papers. Let F be a hyperbolic surface of finite type. That is, F is a surface of genus G with B boundary components and N punctures, such that 2 minus 2G minus B minus N is less than 0. Let pi sub 1 of F be the fundamental group of F. We identify pi sub 1 of F with a discrete subgroup of PSL sub 2 of R, the group of orientation preserving isometries of the upper half plane, block H. The action of pi sub 1 of F on block H is properly discontinuous and does not fix at any point. Therefore, the quotient space is isometric to F. Henceforth, by an isometry of block H, we mean an orientation preserving isometry, and by a closed curve, we mean an oriented closed curve. A homotopically non-trivial closed curve in F is called essential if it is not homotopic to a puncture. By a lift of closed curve gamma to H, we mean the image lift of block R, arrow block H of the map gamma circles pi, where pi are the real numbers into SO1, which is the usual covering map. Every isometry of F of H belongs to one of the following classes. Elliptic, F has a unique fixed point in H. Parabolic, F has a unique fixed point in lowercase delta h. Hyperbolic, F has exactly 2 fixed points in delta h. The geodesic joining of these 2 fixed points is called the axis of F and is denoted by capital A sub F. The isometry F acts on capital A sub S by translation of a fixed positive number called the translation number of F, which we denote by lowercase tau sub F. Since pi sub 1 of F acts on block H without any fixed point, pi sub 1 of F does not contain any elliptic element. Essential closed curves in G correspond to hyperbolic isometries and closed homotopic to punctures corresponding to parabolic isometries. Let X and Y, which are elements of pi sub 1 of F, be 2 hyperbolic elements whose axes intersect at a point capital P, figure 1. By a paper published in 83, theorem 7.38.6, X times Y is also a hyperbolic. Let capital Q be the point in capital A sub X at a distance tau sub X over 2 from P in the positive direction of A sub X, and R be the point at A sub Y at a distance tau sub Y over 2 from P in the negative direction of A sub Y. Then the unique geodesic joining R and Q with the orientation from R to Q is the axis of XY, and the distance between Q and R is tau sub X times Y over 2. And then we see figure 1, which appear to be these points just described, demonstrating the hyperbolic geometry. There is a bijective correspondence between the set of all conjugacy classes in pi sub 1 of F and the set of all free homotopy classes of oriented closed curves in F. Given an oriented closed curve X in F, we denote both its free homotopy class and the corresponding conjugacy class in pi sub 1 of capital F by angle bracket X. Every free homotopy class of essential closed curve contains a unique closed geodesic whose length is the same as the translation length of any element of the corresponding conjugacy class. Given an oriented surface capital F of negative Euler characteristic, the Teichmuller space of capital F, denoted by script T of capital F, is defined as follows. Consider a pair, capital X, comma, psi, phi, phi. All right. In typesetting, it looks like how it should. Consider a pair, capital X comma phi, lowercase phi, where capital X is a finite area hyperbolic surface with totally geodesic boundary, and phi is defined as the mapping of F, capital F onto capital X as a diffeomorphism. We call capital X comma lowercase phi a marked hyperbolic surfaces. Marked hyperbolic surface. We say capital X sub 1 comma lowercase phi sub 1 and the pair capital X sub 2 and lowercase phi sub 2 are equivalent if there exists an isometry I, which is defined as capital X mapped to, well, we don't know if this is bijective. Capital X, arrow, capital X sub 2, capital X sub 1, arrow, capital X sub 2, such that I circle phi sub, capital I circle phi sub 1 is homotopic to lowercase phi sub 2. The Teichmuller space, script T of capital F, is the space of all equivalence classes of marked hyperbolic surfaces. Abusing notation, we denote the point capital X comma phi in script T of F by X, capital X. Given a point capital X in the Teichmuller space of F and a simple closed geodesic X, lowercase x in capital X, we define the Fenchel-Nielsen left twist deformation of X at time S along X as follows. Cut the surface along X and form a new hyperbolic surface, capital X sub S, by gluing the two boundary components obtained from X with a left twist distance of S. We call the Fenchel-Nielsen left twist deformation just left twist deformation. To consider capital X sub S as a point in script T of F, we have to construct a homotopy class of diffeomorphism from capital F to capital X sub S. There are many ways to do this, one of which is the following. Consider a small annular neighborhood, capital N of X. Define a diffeomorphism from N to N, which is homotopic to the twist deformation, and then extend it by identity to the whole surface. Let X be a point in script T of F, and X be a simple closed geodesic in capital X. Let Y be any closed geodesic in capital X intersecting X. Let P be an intersection point between X and Y, and phi sub P of capital X our elements from 0 to pi be the angle of intersection between x and y at P, where the angle is considered anti-clockwise from y to x. From two previously published papers, we have the following theorem. Theorem 2.1. For every intersection point P between x and y, the function phi sub p of capital X sub s is a strictly decreasing function of s. For our purpose, we do not need the full strength of this proposition, which is proved for any geodesic lamination X. The idea of the proof for simple closed geodesic is the following. Consider the unit disk model and suppose X is the horizontal diameter. Now observe that after left twist deformation, the endpoints of the geodesic representative of Y are strictly to the left when viewed from a lift of the intersection point of the endpoints of Y. Goldman bracket. Consider two free homotopy classes of oriented closed curves in a hyperbolic surface F. The Goldman bracket is well defined in the set of free homotopy classes of oriented closed curves, script C. The geodesic representative of each free homotopy class is unique, and the two geodesics always intersect transversely. Hence, we consider the geodesic representatives from the corresponding classes to define the Goldman bracket. The only problem is geodesic representatives may not intersect in double points, but we can modify the definition to avoid this problem. The following algebraic definition is from CG 14 section 3. For the equivalence of these two definitions, see section 3 of CG. Non-cancellation lemma. Given two hyperbolic transformations, x and y, with axes A sub x and A sub y respectively, that they intersect in a point P, let I of xy denote the segment of A sub x of length tau sub x starting from P in the positive direction of A sub x, containing P but not containing x times P. Definition 3.1. Let angle bracket x and angle bracket y be two non-trivial conjugacy classes in pi sub 1 of f. If either x or y is parabolic, define the Goldman bracket of angle bracket x and y equals 0. If both x and y are hyperbolic, let Y be the cyclic subgroup generated by y and define J of x and y is equal to G times Y, which are elements of pi sub 1 of f, over Y, which are I of x, y, intersected with G times A sub y, which are not the empty set. Then the Goldman bracket of angle bracket x, y is equal to the sum of G times Y, which are elements of this function J of x, y, I don't know what this symbol is. Oh, iota. This sum is iota x, y to the G times angle bracket x, y to the G, where iota xy denotes the sign of intersection between the axes of x and y if they intersect and 0 otherwise. Remark 2, the geometric intersection number between a boundary curve and any other closed curve is 0. Therefore, from the above definition, there is no difference between a compact surface with boundary and a punctured surface with the same fundamental group as far as the Goldman bracket is concerned. Hence, we consider only compact surfaces. Section 4. Closed surface versus surface with boundary. Let capital F be a hyperbolic surface with geodesic boundary. To each boundary component delta, we attach a hyperbolic surface of genus 1 with one boundary component of length L of delta by isometry. We call the new surface capital F hat, F bar, I suppose. Lemma 4.1. The inclusion of F into F bar induces an injection from pi sub 1 of F to pi sub 1 of F bar. Proof. Let capital Z denote the collection of boundary geodesics of F in F bar. Consider a hyperbolic metric on F bar such that the length of each element of C is less than the Margulius constant. If a geodesic in F intersects any element of C in F bar, then its length is non-zero, and hence it is non-trivial. Now, suppose G sub 1 and G sub 2 are two elements of pi sub 1 of F, and are conjugate to each other. Then by lemma 4.1, their images in pi sub 1 of F bar are also conjugate. Suppose two terms of the Goldman bracket are the same, that is, conjugate to each other, and they have different signs. If we prove that in F bar they are not conjugate to each other, then by the above reasoning they are not conjugate in F. Hence, it is enough to prove the main result for closed surfaces. Section 5. Lifts of a term in the Goldman bracket with different sign. Let capital X be a point in the Teichmuller space of F. Let X be a simple closed geodesic and Y be any closed geodesic. Suppose P and Q are two intersection points between them such that epsilon of P is equal to negative epsilon of Q, and that xp of y is equal to xq of y. The loop product. Okay. Given any two oriented closed curves, x and y, we always consider the angle at intersection point to be the angle which is in the positive direction of both axes. For any point x, which are elements of script t of f, we denote phi sub p of x and phi sub q of x to be the angle of intersection between x and y at p and q in x. The lift of a term of the loop product of x and y in the upper half plane passing through a given lift of the point P is a bi-infinite polygonal path. This polygonal path is quasi-geodesic and therefore follows a unique geodesic. We consider this geodesic to be the axis of the lift. Consider lifts of the loop products of x and y and the loop products under Q of x and y to the upper half plane, H. As they are freely homotopic, they are conjugate to each other. Therefore, talking conjugate, if necessary, we assume that they have a common axis, and the axis is the y-axis. The lift of the loop product x and y, this is figure 2, the left-hand side where epsilon of q of 1 equals negative y, and the lift of x of q of y on the right-hand side where epsilon p of 1 equals 1. We consider the anti-clockwise orientation in the upper half plane. If capital P and capital Q are lifts of P and Q, such that the common axis of the lifts of the loop product of x and y and x of x and y in both p and q is the capital y-axis, then the lifts look like a bi-infinite polygonal path as in figure 2, where lowercase l sub capital X of a sub 2 of capital Q sub 1 is equal to lowercase l sub x of b sub 2 of capital P sub 1, which is equal to tau sub y over 2, and L sub x of A3 and Q1 is equal to L sub x of B3 and P1, which is equal to tau sub x over 2. Also from the geometry of product isometries, we have L sub x of the loop product of x and y under Q over 2 is equal to L sub x of A2 times A3, which is equal to L sub x of B2 times B3, which is equal to L sub x of x loop product y over 2. And these points are intersections with the axis in the lift. Therefore, by symmetries of the triangles, we have phi sub q of capital X is equal to phi sub p of capital X. As X is an element of the Teichmuller space of F, as it being in the space is arbitrary, the above equation holds for all X. Proof of the main theorem. We prove the following lemma, from which the main theorem follows. Lemma 6.1. Let F be an oriented surface of finite type with negative Euler characteristic, and X and Y be two oriented closed geodesics intersecting each other. Suppose X is a simple geodesic. If P and Q are elements of the intersection of X and Y, such that epsilon of P is equal to the negative epsilon of Q, then the loop product of X and Y in P is not equal to the loop product of X and Y in Q. Figure 3. Two lifts P and Q of the points P and Q into the upper half plane. If we consider the anti-clockwise orientation of the upper half plane, then the sign of P equals 1 and the sign of Q equals negative 1. Proof. We prove by contradiction. Suppose that the signs are opposite and that the loop products are equal. As they are freely homotopic to each other, their lifts are conjugate to each other by an element of pi sub 1 of F. Let X be any point in the Teichmuller space of F. Then, from equation 1, we have phi sub p of x is equal to phi sub q of x for all x in the Teichmuller space of F. Let x sub s be the point in the Teichmuller space of F obtained by a left twist deformation after time s from x along x by figure 3 and theorem 2.1. Phi sub p of capital X sub s is equal to pi minus phi sub p of x sub s, and phi sub p of x sub x is equal to phi sub q of x sub s, and both of the functions are strictly decreasing. Therefore, phi sub p of x sub s is a strictly increasing function, and phi sub q of x sub s is a strictly decreasing function, as phi sub p of x sub 0 equals phi sub p of x, phi sub q of x is equal to phi sub q of x sub 0. We have capital phi sub p of capital X sub s does not equal to capital phi sub q of capital X sub s for all small s on 0 to pi, a contradiction. References: The Geometry of Discrete Groups, Bearden, 1983. Chas and Gagdiel, The Goldman Bracket Determines Intersection Numbers for Surfaces and Orbifolds, 2014. Chas, Combinatorial Lie Bialgebras of Curves on Surfaces, 2004. Chas and Krongold, Algebraic Characterization of Simple Closed Curves via Turev's Cobracket, 2010. Minimal Intersection of Curves on Surfaces, Chas, 2010. Chas and Krongold, An Algebraic Characterization of Simple Closed Curves on Surfaces with Boundary, 2010. A Primer on Mapping Class Groups, Farb and Margalit, 2011. Invariant Functions on Lie Groups and Hamiltonian Flows of Surface Group Representations, Goldman, 1986. Fuchsian Groups, Katok, 92. The Nielsen Realization Problem, Kirchhoff, 1983. The Goldman-Turev Lie Bialgebra and the Johnson Homomorphisms, Kawazumi and Kuno, 2013. Foundations of Hyperbolic Manifolds, Ratcliffe, 2006. Sky and Quantization of Poisson Algebras of Loops on Surfaces, Turev, 1991. On the Symplectic Geometry of Deformations of a Hyperbolic Surface, Wolpert, 1983.